So welcome back to the afternoon session. The first talk of this afternoon is Sangmin Choi that will tell us about logs of theorems and asymptotic symmetries. Thank you.
Thank you. Right, so I'd like to start by thanking the organizers for putting together this great workshop and for the opportunity to have me present my talk here. I'll be talking about the relationship between something called the logarithmic self-theorems and asymptotic symmetries. And this is based on a number of papers that I've put out with my collaborators, Andrea Pum, who's in the audience. Alok Lada, he was planning to be here, but unfortunately he couldn't make it. Yes. All right, so let's begin. Over the past decade, we have uncovered a remarkable correspondence between self-theorems in quantum field theories and asymptotic symmetries of the theory. And the correspondence is this. A self-theorem is nothing but the word identity or the law of charge conservation of the asymptotic symmetry generators. And in this holds in scattering processes, in particular, if you sandwich the commutator between the generator and the S matrix between in and out states, then this quantity is zero. And this is just a clever rewriting of the self-theorem that corresponds to this symmetry. And this has been worked out case by case over the past years. For instance, the large gauge transformation in massive and massless QED or superphase rotations. Their word identity correspond to subleading soft photon theorems. The BMS super translations, its word identity is nothing but the leading soft graviton theorem. And there's also symmetries whose word identities are the tree-level subleading soft theorems. This correspondence extends to symmetries in higher dimensions, symmetries with supersymmetry, and so on and so forth. There's numerous examples, and although this correspondence is being studied on a case-by-case basis, this seems to be quite robust. And just because this will be relevant for us, I'll just schematically illustrate how this correspondence works. So if you have a soft graviton theorem, let's say for concreteness we work this out for superrotation. I'll ignore any prefactors of 2's and pi's and minuses. So you write down a leading and subleading soft graviton theorem at tree level. It takes the following form. The amplitude of the m plus 1 point amplitude with the soft graviton. If you expand it in this energy of the soft graviton, there's a 1 over energy pole, and then there's a finite term. So the amplitude factorizes into the soft factor, multiplying the n point amplitude without the soft graviton. Now, given a symmetry, in this case superrotation, you compute its generator in the future and past infinities using methods, for instance, like covariant phase space method. And then the charge splits into the so-called hard and soft parts. And by making a judicious choice of the parameter vector field, it turns out that the action of the hard charge on the in and out states precisely give you the soft factor multiplying the n plus n point amplitude. And then the soft charge is essentially a soft graviton insertion, making it an m plus 1 point amplitude, followed by some specific projection onto the energy space, such that when combined, it gives you an expression like this. So the m plus 1 point amplitude, you take some projection, gives you the subleading soft factor. And this projection works in such a way that if you have this soft expansion in a series, it picks out exactly this subleading soft factor. And this, although this was just for superrotations, this is in general how things work for this correspondence. Right, so that was at tree level. And soon after the paper of Strominger and Gazzazo on the subleading soft graviton theorem at tree level, in 2014, there was a paper put out by Swinburne and his collaborators, Davis and Knoll, that found a one-loop exact correction to the subleading soft factor. the problem was that this this correction to the subleading soft vector was infrared divergent. So if you do dim reg, this correction comes at order 1 over epsilon. So this is quite confusing because we know that amplitudes computed using Fox states are infrared divergent, but it's hard to understand how to understand an equation that has both infinities on the left and right-hand side. So does this mean the soft theorem is ill-defined? A couple years later, in 2018, Biswajit Sahu and Ashok Sen put out a paper saying that this problem actually seems to be a consequence of assuming a power series in the soft energy expansion. And if you actually look at the Feynman diagrams at one loop, they found that there must be an additional non-analytic term in between the leading and the subleading tree-level soft theorems. And that additional term should go as logarithm of the energy. And they also found that this new term is also one loop exact. And because we will be looking at gravity, just for illustration, this is what the soft vector looks like. There are more nice ways to write this, but I've split this into 2 parts. So this logarithmic soft vector, and also the one for QED, usually splits into 2 parts. One, the so-called classical log soft vector, and the one that's called the quantum log soft vector. And the reason these names are given is because the classical soft vector you can derive just by solving equations of motion perturbatively in the coupling constant without doing Feynman diagram computations. So just doing classical scattering amplitudes, you can compute the classical part. But if you actually compute Feynman loop diagrams, then you get the whole collection of the classical and the quantum part. And here the beta is just the relative velocity of the particles. J is the usual angular momentum operator. That's like derivative in the momentum space. I would like to illustrate some origins of these terms here. So both in the classical and quantum part, the first terms have to do with the interaction of the massive scalar field, external scalar fields, with the soft graviton. But on the other hand, the second terms here come from the interaction of the one loop graviton with the external soft graviton. So in that sense, these terms are, the second terms in both equations are usually referred to as the gravitational drag. It's the drag, it's the internal loop gravitons dragging this external soft graviton. And this is an effect that you only see in gravity, not in QED. Okay, this new logarithmic term in the soft expansion is often referred to as the logarithmic soft theorem, logarithmic soft photon graviton theorem. So there's a new soft theorem. And the correspondence between asymptotic symmetries and soft theorems strongly suggests that this is the word identity of an asymptotic symmetry. And there has been a few papers in the literature in this direction, which include, for instance, many of the authors are in the audience. There was the Complete Galata paper in 2019, which studies massive QED. And what they do is they study the effect of long-range interactions of fields on the fall-offs of the fields and construct a charge, which, if you write the conservation equation, will land you right on the logarithmic soft photon theorem. And then there was the paper of Atul Bakhar a couple of months later, which extends this result to massless QED coupled to gravity. And then there was, in the latter 2 papers, Soneinu and Rutikoni and Agrawal, they study the 1 over epsilon corrections to the superrotation word identity and collect these infrared divergent terms. And what they found is that if you replace the 1 over epsilon, the regulator, with the logarithm of the external soft graviton energy, then you land on the soft factor that Ashok Sen and Biswajit Sahu wrote down for the case of logarithmic soft graviton theorem. So what I would like to show in this talk is that if this correspondence indeed holds, then we should be able to just work through the covariant phase space formalism without much input, and then have the soft theorem land us on a projection operator that picks out the log omega, and then the hard part giving us exactly on the log soft factor in such a way that if we could do this computation before 2018, when the logarithmic soft theorem was written down, we would have figured out that maybe there should be something that goes like the log of the energy that's missing in the soft energy expansion. And we should, in addition, be able to find out that this correction is one loop exact just by solving equations of motion. So this is what I would like to convey in this talk. I'll show you that when doing covariant phase space analysis, if you take long-range interactions seriously and compute the asymptotic behavior of the fields, this will naturally give rise to the logarithmic soft theorem. And for concreteness, we'll consider superrotations in a theory of massive scalar particles coupled to gravity, in the sense that we put the background to be flat space plus gravitons. But a similar story also follows for massive QED. So before I begin, any questions so far?
So sorry, just to understand, the eventual message is there is an underlying asymptotic symmetries for the logs of theorems, or no?
Sorry, can you repeat that?
There is an underlying asymptotic symmetry explaining the logs of theorem, or
no? No, this is superrotations, the same asymptotic symmetry that would give you the tree level.
It's not a new one.
It's not a new one, yes. At some point we suspected maybe that was the case, but it turns out to be not the case. Yes. Any other questions? If not, let's begin. So superrotations on the time like infinity, which I'll write I plus. The superrotation itself was worked out by Kempik and Lada a couple years back at tree level for massive particles on time like infinity. And in order to study massive particles, we want a nice coordinate system to resolve the time like infinity. And the one that we'll be using is the hyperbolic coordinates. So these are related to the Minkowski coordinates in this way. And we take tau to infinity while having rho fixed. This coordinate system is very nice in the sense that each particle with an asymptotic momentum p lands at one point on this manifold, 1 point in these coordinates. And this is in a similar spirit to how every null ray hits 1 point on scry. And then, in these coordinates, a superrotation is given by a vector field on this hyperboloid that is generated by the vector field on scry. And it's given by just smearing the sphere vector field with a vector bulk to boundary propagator of radius 3 in Euclidean signature. And we want to work with the asymptotic form of the fields. And to do this, we don't assume a priori any fall-offs. What we do is we start from the free fields of gravitons and scalar fields, and we plug them into the equations of motion. So we take the free scalar field, we compute the energy momentum tensor, we plug it into Einstein equations. Then what we find is that actually there's a sourced graviton field that goes like 1 over time. That there's a specific form here. Maybe some people will recognize this, this form of the Green's function, which seems to be universal for the behavior of massive particles and its action on gravitational fields. We take this graviton field, plug it back to the Klein-Gordon equation, which now becomes Klein-Gordon equation in curved spacetime. We solve for the scalar field. We find that it gets an overleading correction that's logarithmic in time. Now we take this, compute the energy momentum tensor again, plug it into Einstein equation. So we can do this perturbatively in every order in the coupling. And when we do this, we find that the scalar field actually has a leading term acquiring a phase that diverges logarithmically in time. There's a subleading term that goes like 1 over tau 5/2. It also has an infinite number of logs, but unfortunately, at the moment, I don't see how that can easily exponentiate or have any simple explanation. Now, we take these fields and compute the superrotation charge using covariant phase space method. What we find is that the charge itself is divergent. So we introduce an infrared scale lambda such that tau doesn't go to infinity, but instead it goes to lambda inverse. Then we can have the charge to be log of the scale times some coefficient. The coefficient takes the following form. And because we have done this to all orders in the coupling and found that there's only the one loop term, this expression is one loop exact in this sense. Yes. Okay, the soft charge. Just like how the scalar field was quote unquote dressed by the gravitons, the graviton itself also gets dressed by gravitons. And one can, of course, do this by solving Einstein equations. An easier way to do this is to put a photon in a curved background and see how gravitons dress this photon. And by equivalence principle, gravitons will get dressed in the same way. And what one finds is that the shear gets shifted in this particular way. I haven't written down an expression for H naught here, but this is just another sourced graviton on scry, just like H tau tau. The first term is the expression that you would see for soft superrotation charge computed using free fields. Now you could say, okay, we have a divergent term, maybe this is finite. But what actually happens is if you solve equations of motion, what one finds is that because of the massive fields on I+, they talk to the shear tensor on the future boundary of scry. So if you solve Einstein equation on this sphere, what one finds is that the number of powers of logarithms in the energy momentum tensor is closely correlated with the number of log of time of the shear at large U. And actually, the exact correspondence is such that each log, the nth log tau, sources the nth log U. And using the expressions that we had before to all loops, we can compute the energy momentum tensor to all orders in the coupling constant. What one finds is that there's only one log tau. So you could think, okay, so that means we have the shear at large U behaves like log U over U. But actually, the coefficient of log U over U is precisely the del mu t mu nu, which is the momentum conservation, and that vanishes. So it turns out that the large time behavior of the shear is a constant term that you would see classically, but then there is a 1 over U correction. And because this expression has a derivative and a U, a 1 over U would become 1 over U squared, and then 1 over U again. If you integrate that, you get a logarithmic divergence. So this term is also logarithmically divergent. We regulate this, again, by using a large time cutoff. But now you'd be worried that, okay, we regulated tau to be lambda inverse, but U could be linearly dependent on tau, but the proportionality constant is not exactly 1. But this in gravity is fine because this is sitting in the logarithm. So any proportionality constant you can push into the finite part. And therefore, we can be cavalier about using different cutoffs for different coordinate systems as long as they depend linearly to each other. And when we regulate this divergence, what one finds is that it effectively changes the U partial U to partial U, U squared partial U. And collecting this and the shift that we saw earlier, the soft charge, we can write down as log of the cutoff times this expression here. And again, this was done to every order in the coupling constant, and we only find a one loop effect. And therefore, this expression is also one loop exact. So the total superrotation charge takes the following form. There's the hard charge and the soft charge given here. Remember, this was the the H1 tau tau comes from the interaction of matter to gravitons. This thing here came from the coupling of gravitons with gravitons. So what happens is that when you plug it into the word identity, this gives you all the terms that has the matter-graviton interactions. This term gives you the gravitational drag term. And then what remains is a graviton insertion with a particular projection in the momentum space. And you can see that there's these divergent logarithm of regulators. We can divide by this and get a finite word identity. So while the charge itself is infrared divergent, we get a finite word identity. And it turns out that if you collect the coefficients of the logs, the word identity of superrotation turns out to be exactly the classical log-Soft theorem. And here it is classical because in solving all equations of motion, we've used retarded propagators. And there should be a straightforward way to extend this to the quantum case, and some of this was demonstrated for massive QED in the paper of Kempik and Lada in 2019. And here I want to emphasize that this projection here kills all powers of omega. So if we didn't know a priori that log-Soft graviton theorem existed, and we stumbled upon this computation, we would think, okay, we have a projection which kills all powers, so there must be something else. And if you start including powers of logs, actually, this projection picks out exactly one log omega. Therefore, this can be thought of as an independent derivation of the classical log-Soft graviton theorem. Okay, so I want to hammer home here some points here. So we started from free fields. We didn't impose any fall-offs. We had no choice. We plugged into equations of motion. It gave us a solution which has to be the asymptotic form of the fields. And once we take those fields and compute the superrotation charge, the charge diverges. But you can regulate this and then write down a finite word identity. And that word identity has a projection to log omega, which shows that there really is a logarithm of energy in the soft expansion. And then all the remaining terms organize to the classical log-Soft factor. And because we could do this, the split to I plus and scri plus was very nice in the sense that we could do this computation to arbitrary order in the coupling. And they all sum up to be 0 except that one loop effect. And therefore, this computation can be thought of as an independent demonstration that this log-Soft theorem is indeed one loop exact. I'm not sure how I'm doing with time, but that is it.
Perfect.
Thank you.
Could you show the piece? Could you show the piece where the charge was B daga B,
Oh,
Y?
yeah.
No, already was there.
Oh, it was here.
Yes.
Yes.
QH log.
QH
Is
log.
there any intuition for the term Y alpha, D alpha, H tau tau?
Yes. So the Einstein equation gives you a second-order differential equation for H1 tau tau on the hyperboloid. And if we solve this by Green's function method, it gives you this here, the sigma, yeah. So the hyperbolic, sigma is the hyperbolic cosine of the geodesic distance between the points y and y prime on the hyperboloid. So when this b dagger b hits, remember each momentum hits one point on the hyperboloid. So these points can be thought of as momentum, characterizing the momentum. So when it hits a Fock state of momentum p and p dagger, this becomes p dot p prime minus 1/2 p squared p prime squared. So actually, maybe it's better to see this. That actually becomes exactly this. It's not immediately clear from this from beta, but if you write it out in terms of P's and PA and PB, this thing here is exactly the expression sitting here. And the judicious choice that we make for the vector field makes it such that, where is it? This y alpha del alpha becomes the tree-level subleading soft graviton factor, which is actually the thing that is acting right here. So this becomes y alpha del alpha, and this is that Green's function sitting in h1 tau tau. So this is h1 tau tau, this is y alpha del alpha.
You also comment about solving the equation of motion.
Yes. Oh yeah, so this comes from solving the equation of motion, the Einstein equations for h tau tau.
Okay.
Yes.
Okay. After your presentation, I get a bit puzzled about the covariance of your procedure under super rotations. Because as far as I see your formulas, you are choosing a particular frame on the celestial sphere, right?
A particular frame on the celestial sphere.
Yes.
Yes. Like no super translation for charges, for instance. There's
No, but no. I mean a super rotation frame on the celestial sphere. So I was wondering if you change this frame, how do your result change?
Oh, so one important thing that we are using here is we are expanding on flat space. So we have eta mu nu plus kappa h mu nu, and the h mu nu is the graviton. If you do super rotation, maybe like the sphere metric won't be sphere anymore. It'll be turned to something else. But I think while the computation could be a little bit different, it should, at the end of the day, be the same result.
Okay, because I think that something important in your argument is that you are computing the pure super rotation charge, but you know that it turns on a linear term in U in the shear that you completely discarded here on your slide. So you say that if you encode this field, this additional field, everything will transform covariantly, or you have some control on the transformation of your result.
That is something that we haven't thought about, but so you mean like quadratic terms, for instance? Those are not here.
No, it's a linear term. It's just that C is U news vacuum of the news tensor of the vacuum plus what you wrote, basically.
I see.
And that's important because when you are computing integrals over null infinity, you have this additional divergence that can mess up a bit the things. That's why I'm pointing out that actually your boundary conditions for the shear are missing this important piece if you want to address super rotations.
Yeah, maybe we are working, because you're working in a particular frame, we are missing on these.
Yeah, okay.
But I'd be happy to talk about more on this.
Okay. Thank you.
No, I just wanted to say that, indeed, you can choose a frame in which black is zero, and it's not a covariant computation.
Yes, but then you should ask if what you are doing can be, or you forget about super rotation, and I maybe, but since you are forgetting about super rotation, you have to ask this. Question is fundamental.
Yeah, maybe I have a related question. Like, what happens if you compute the Barnich-Trossard bracket of two of your charges?
The Peirce bracket of...
The Barnich-Trossard bracket?
Oh. Actually, the charge...
Because there's an argument that, if your construction is covariant,
Yes.
you should get no cocycle, no field-dependent cocycle, so...
Actually, so the hard charge here is quartic in the matter field operators. So quartic operators, if you do compute brackets naively, you don't see that it closes.
Okay, so maybe that's a sign.
Maybe this is related. But.
Any more questions? Yes.
Can you get higher order in log, omega log omega square? And
yes, I think this method is suited for that purpose. So, for instance, like the infinite tower of logs of theorems, we could probably tackle in the same way using different asymptotic symmetries.
You have done this or not?
No, this is work in progress. Yes.
Okay.
Can
you resum all this log or not?
Oh, yeah. So resummation for the massive QED, for instance, is very straightforward. It's just more terms. But this can be done, and we are looking into what it looks like in the next order in the logs. But they can be resummed. They don't exponentiate, but still we can work with the expressions at arbitrary order. Yes.
But for graviton, it's exponentiate.
Oh, in graviton, there's one more complication, which is at this order, luckily, the graviton energy momentum tensor didn't contribute to any of the computations because they fell off too fast. But at the next order in the log-soft theorem, we expect that they would come in, and that would probably alter some more things that we could take for granted here. So we really have to work out like what it looks like. But I think it principally can be done.
Thank you.
So let's thank the speaker again.
Thank you.